Information in its raw state is a collection of ambiguous signals. Without a processing framework, these points remain a cloud of noise. In academic research, attempting to extract truth directly from this noise leads to misinterpretation. One might see patterns where only random fluctuations exist. When these interpretations are accepted without scrutiny, they corrupt academic decision-making and spread conclusions that do not reflect reality. To prevent this, researchers engineer a methodological system. This structure acts as a mechanical filter designed to separate objective facts from researcher bias. Data gains functional utility only once a verified system proves that the numbers actually represent what they claim to represent. Establishing research quality requires an architectural system divided into two distinct parts. The first part is methodological precision. This ensures that the tools used to collect data operate with mathematical consistency. The second part is a foundation of moral principles. These rules govern the interaction between the researcher, the participant, and the data itself. This schematic models the relationship between these elements. The two measurement pillars, validity and reliability, rest on the base layer of ethics. If this ethical foundation fails, the pillars instantly shatter. The metrics lose all meaning if the study's moral integrity is compromised. High-quality research is the result of the deliberate intersection between exact science and strict morality. We begin with the first pillar, reliability. Reliability measures consistency. It identifies whether a tool produces the same results when applied to the same conditions over time. A reliable tool is immune to random chance. If an experiment is repeated multiple times, the results will remain stable across every iteration. This target board illustrates high reliability in isolation. The data points strike in a tight, consistent cluster, showing that the tool is operating predictably. Because the instrument hits the same spot every time, it meets the technical definition of being reliable. However, consistency does not guarantee that the tool is measuring the correct variable. The cluster is stable, but it is nowhere near the center of the target. A reliable tool can lead a researcher toward a false conclusion if that tool is incorrectly calibrated or aimed at the wrong objective. To correct for this, we introduce the second pillar, validity. Validity is the measure of accuracy. It confirms the link between the measurement tool and the theoretical concept it is intended to capture. On this target, we see both pillars working together. The results are consistent, but they are also accurate, striking the bullseye precisely. Researchers verify this by checking content. They check for construct validity, and finally, external validity. Each check ensures that the tool is relevant to the subject and applicable to the wider world. This exam paper illustrates a failure of validity. While it may be a functional test, there is a structural mismatch between its stated purpose and its actual content. Using this test will produce consistent numerical data, but those numbers fail to provide any insight into the student's actual mathematical ability. Without validity, a study is merely an accurate measurement of the wrong reality. Once tools are verified as valid and reliable, the focus moves to the analysis of the resulting data. Objectivity requires that data be analyzed based strictly on documented facts. The researcher must remain neutral, preventing personal opinions from shaping the interpretation. This objectivity allows for generalization, which is the process of applying verified findings from a small group to a much larger population. Here, we see how a single node of verified data scales. The glow expands outward to illuminate the entire network of identical nodes. This expansion is scientifically valid only if the initial sampling technique ensured that the small cluster truly represented the whole. True scientific value is achieved when objective data can be safely applied beyond the specific confines of the study. Methodological precision is of no use if the data collection process is destructive to the subjects involved. Research ethics act as the moral governance of the study, regulating how participants are treated and how their data is managed. One primary protocol is informed consent. This ensures that participation is voluntary and based on a clear understanding of the study's goals. Furthermore, scientific integrity demands total honesty. This includes the absolute prohibition of plagiarism and the manipulation of results. The rule of avoidance of harm ensures that no physical or psychological damage is inflicted on those who contribute to the research. An ethical violation is more than a moral failing. It compromises the integrity of the data and can render the entire study unusable. Designing an ethical study requires a precise understanding of technical terms. Many researchers incorrectly use the terms confidentiality and anonymity interchangeably. Ensuring data is kept secret is legally and structurally different from ensuring a participant's identity is unknown. On the left, we see confidentiality. The researcher knows the participant's identity but secures it within a locked system to prevent public disclosure. While safe from outside eyes, the link between the individual and the data remains intact. On the right, we see anonymity. Here, identifying markers are destroyed at the point of collection. The researcher cannot link the data back to the individual. Understanding this mechanical difference is necessary for building a methodology that truly protects the participant. Evaluating a research paper requires an audit of the processes used to generate its results. This 4-point diagnostic matrix allows us to deconstruct a study and verify its quality. First, we ask, are the measurement tools valid? We must determine if they actually capture the concepts they claim to measure. Second, we check for reliability. If this experiment were repeated tomorrow, would the results be consistent? Third, we examine the ethics. Was the data gathered honestly, and were the participants protected throughout the process? Fourth, we look at the methodology. Was the overall design and analysis appropriate for the population being studied? A study must satisfy all 4 criteria. If it fails even one, the findings cannot be accepted as objective truth. As a member of the scientific community, the primary responsibility of a researcher is the critical evaluation of these 4 points. Ethics must always provide the foundation, while both validity and reliability determine the final quality of the scientific output. Research quality is defined by the engineering of a system where findings are verified, transparent, and ready for rigorous scrutiny.